Good afternoon, everyone, or good morning for the other participants in the other continents. My name is Horia Petran, and I have the pleasure to welcome you to the fourth session of Panel 8, Buildings. We had 3 sessions last days, very good sessions, but I'm confident that this will be better. And the topic for today is methodologies for better decision and quality towards carbon neutrality in buildings. We have a set of fine speakers today. First, we will have a presentation from Marcos Tenente from Institute for Systems Engineering and Computers, INES, at Coimbra in Portugal, presenting a novel approach for assessing the multiple benefits of energy efficiency technology. Then we will have Daniel Kerr from the Montfort University in the UK, research assistant, speaking about how low carbon retrofit affects summer comfort. And then we will have, I would say, a team from Plymouth University in the UK, Julie Goodhue and Matthew Fox from the School of Art, Design and Architecture in the Plymouth University, describing how nearly zero defect buildings can achieve nearly zero energy buildings. And then we will have Agneta Persson, Managing Director of Anthesis in Sweden and President of the European Council for Energy Efficient Economy, eceee. Speaking about decentralized ventilation systems with heat recovery, would that be a solution for NZ? So that being said, just the technical details. All the presentations are pre-recorded, so we will follow the presentations. That will take 15 minutes each. And after each presentation, we will have 5 minutes of question and answers. And hopefully at the end, we will have like 10 minutes to an overall discussion and some unanswered questions. So this is the point when I think we can watch the first presentation from Marcos.
Hello everyone, my name is Marcos Tenente. I'm a PhD student at the University of Coimbra and researcher at INES Coimbra, and I'm here to present to you a novel approach for assessing the multiple benefits of energy efficiency technologies. In first place, I will give you a brief introduction about the problem we are addressing today. Then I will show you the objective of this work. Later on, I will explain our methodology and its application to a Portuguese case study, followed by the results obtained, and finally, I will disclose our conclusions. The European Union building sector accounts for about 40% of energy consumption and 36% of greenhouse gas emissions. In Portugal, the building stock is mainly composed of residential buildings, and about 2/3 of these were built before the introduction of energy efficiency requirements for new buildings in 1990, showing low energy performance levels. Furthermore, approximately 33% of the building stock built before 2012 reveals repair needs on the roof and exterior facades. To tackle this kind of problems, the European Commission created several energy efficiency and climate policies and established several targets to be fulfilled by the European Union countries. Portugal, in order to comply with the European Union policy, adopted several programs aimed at funding energy efficiency projects. However, these are usually based on a cost-benefit approach and often relies on energy and greenhouse gases savings during the operation period. Two other issues related with this kind of programs are that the assumptions considered are usually selected by the analysts and in some way even in the computation, and the holistic approach are not frequently used in the assessment of the impact of investing in energy efficiency technologies in the residential sector. Therefore, the objective of this work is to develop a methodological framework to evaluate energy, economic, environmental, and social impacts of adopting certain energy efficiency retrofit technologies in the Portuguese residential sector. This approach will be applied from the manufacturing to the operation phase. Said that, the methodological approach proposed here is an integration of input-output lifecycle assessment model with a thermal dynamic simulation. Hybrid input-output lifecycle assessment is itself a combination of process-based lifecycle assessment with economic input-output, which will take advantage of these methodologies' advantages, simultaneously avoiding their drawbacks. In our approach, hybrid input-output lifecycle assessment will be used to assess the energy, environmental, economic, and social impacts of energy efficiency technologies that will replace the less efficient ones, considering manufacturing, packaging, installation, and maintenance lifecycle phases. Thermal dynamic simulation will be used to assess the energy needs of households during its lifespan. The application of this approach is divided in three steps. First, we have defined the system boundaries through the identification of business as usual technologies used in the residential sector and the best available technologies that will replace them. Then, we selected the representative households for our case study, and finally established the life cycle phases addressed. In second step, we applied the hybrid input up to output lifecycle assessment by computing the investment in best available business as usual and best available technologies. Then we decompose the life cycle phases into components by gathering data on share of components costs and remove the imports. After that, we compute the component's total output by relating the total expenditure to each component and with the corresponding products of supply and use tables. And finally, we compute the domestic impacts and savings by combining the impact multipliers with the domestic output vector. In third step, we apply the thermal dynamic simulation to compute the energy needs for space heating and cooling before and after installation and compute energy savings. In order to validate our methodology, a single dwelling built between 1961 and 1991, located in the region of Coimbra, which is a moderate climate zone, was chosen as a case study to simulate the implementation of different retrofitting strategies involving the replacement of lighting systems and the application of two types of insulation with different thicknesses. For representative purposes, the results will consider 15,000 dwellings with the same typology and located in the same area. This single dwelling has one floor with one kitchen, one living room, two bedrooms, and two bathrooms. In this work, the energy retrofitting strategies and scrutiny involves a replacement of a compact fluorescent lamp of 18 watts by a LED lamp of 14.5 watt in the kitchen and living room, the replacement of a 14 watt CFL lamp by a 10 watt LED lamp in each bedroom and bathroom, and two types of insulation, the expanded polystyrene EPS and the insulation cork board ICB with distinct thicknesses, 40 millimeters, 100 millimeters, and 140 millimeters applied to the roof and facades. The reason behind the choice of these thicknesses in until 140 millimeters relies on the fact that it allows meeting and even exceeding the minimum energy requirements set out by the Portuguese Energy Performance Regulation of residential buildings, and because there is a lack of available data for higher levels of thicknesses. The energy, environmental, economic, and social impacts assessed in this study are the energy consumption, greenhouse gases, acidifying gases, ozone precursor emissions, waste production, gross value added, and employment. According to our analysis, The replacement of CFLs with LED lamps will bring environmental and energy benefits at the expense of economic and social benefits. As shown in the table during the manufacturing packaging phases, LED promotes a decrease of emissions of about 90%. The waste generation and embodied energy were reduced about 85%. Nevertheless, the gross value added created and the employment generated will also decrease about 83%. The reason behind these results can be twofold. LED electronic components, which represent a big part of the LED costs, are mainly imported, and the number of CFLs that needed to be manufactured during the lifetime of the building is 2.5 times bigger than that of LED lamps. Lighting technologies, installation and maintenance costs were neglected since their replacement is usually done by the owner or the tenant of the dwelling. During the operation phases, the energy consumption reduced about 24% with this substitution. In the case of insulation, it was assumed that it can be installed in the facades or in the roof. With the dynamic simulation, it was possible to ascertain that without insulation, the estimated energy use would be about 4 terawatt-hour after half a century of operation of the 15,000 buildings. When EPS and ICB are applied to the facades, the energy needs for heating and cooling become lower with EPS with 140 millimeters of thickness, and the second best value is obtained by ICB with the same thickness. Comparing the impacts of the early stage of life cycle, investing in ICB allows increasing the gross value added about 800%, employment about 422%, although emissions and embodied energy also grew about 300%. When the roof is insulated, the results regarding the comparisons have similar orders of magnitude. For simultaneous insulation of roof and facades, the lower value for energy needs is obtained by the combination of EPS for facade insulation with EPS for roof insulation, while the second lowest value regarding the energy requirements is obtained by the combination of ICB for facade insulation with EPS for roof insulation. When contrasting these two cases, the latter doubles the gross value added and increases by 60% the number of jobs created, while producing nearly 35% more emissions and has 40% more embodied energy than the former. If the components of lighting technologies were entirely produced in Portugal, it would mean that gross value added and employment would be nearly 3 times bigger. However, this also mean that emissions and energy consumption would double and the waste generation would grow about 150%. Regarding the insulation, when we compare the facade and roof insulation, the VPS would generate up to 8 million euro of gross value added, 175 jobs, more than 2,800 tons of greenhouse gas emissions, 600 tons of waste, and 12,000 megawatt hour of energy consumption. In the case of ICB, in the same scenarios, it would not bring significant domestic effects because the process behind its production is almost 100% Portuguese. Considering the last scenario, the use of EPS for facade and roof insulation would nearly double the economic and social impacts, would double emission production and embodied energy, but it would increase the waste production almost 300% regarding the EPS, which considers imports in its life cycle phases. Regarding the use of ICB for facade insulation with EPS for roof insulation simultaneously, it would increase economic and social impacts by 1/3, increase emissions and embodied energy by 60%, and would double the waste generation. Therefore, our conclusions are: this paper presents a novel methodological approach that integrates the use of hybrid input-output lifecycle assessment with thermal dynamic simulation to assess the energy, economic, environmental, and social impacts of adopting different retrofitting strategies in Portuguese residential sector, considering the manufacturing, packaging, installation, maintenance, and operation lifecycle phases, also enables policymakers to evaluate which are the best technologies to be funded using holistic perspective, and also can be adapted to any kind of technologies in any country. The results for lighting technology suggest that the replacement of CFL with LED lamps will decrease either economic and social benefits, as well as the environmental and energy impacts, since the electronic components of LED lamps are mainly imported, and because the number of CFLs used during the lifetime of the buildings are more than twice the number of LED lamps needed for the same period. During the operation phase, the replacement of CFLs by LED lamps will save up to 14,500 megawatt hour in energy consumption. Regarding insulation, we have concluded that investing in the EPS is cleaner but more energy intensive than ICB, also generating a lower number of jobs. If the components of the retrofitting technologies under scrutiny were entirely produced in Portugal, lighting technology would promote gross value added and employment growth beyond the rate of increase of emissions, waste generation, and energy consumption. On the other hand, in the case of EPS, the rate of growth of the environmental impacts and the embodied energy would be bigger than the remaining benefits. For the case of ICB, its production would not bring significant domestic effects because it's almost 100% Portuguese. Since energy savings obtained will increase the real household income, the so-called rebound effect is expected, which can be assessed in the future. Also, future work is currently underway to further detail the information collected regarding the share of costs and materials to increase the level of disaggregation of the economic sectors of supply and use tables. The methodology will also expand it to other types of retrofitting technologies and will encompass the end-of-life phase. If you have any questions, feel free to ask, or you can contact me by this email. Thank you.
Thank you, Marcos, for this presentation. Quite interesting and quite a good approach. We often forget about the life cycle assessment. We concentrate on the operational phase, but by trying to reduce the carbon footprint on the operational phase, we are increasing the total carbon footprint. I have only one question. Of course, there are multiple benefits, also direct and indirect, that could be taken into account. For example, the indoor environment and health improvement and the cost of health improvement and so on. But I saw that you're concentrating in your approach until the phase of operation. So after the end of life, this is the based on, is included in the continuation of work, as far as I saw, because of the recycle, the reusing, and the disposal are also important.
Yeah, thank you for the question. Yes, the end of life is not included in this work because this work is initial, and we select just some installation technologies and lighting technologies just to show how this methodology is used. But in further work that we are developing now, we are considering other types of energy efficiency measures, like space and cooling spaces, space heating and cooling, sorry, domestic water heating, and also as further work, we are trying to to consider the end of life phase. Now we are not have enough data available for the end of life, and that's why we are not considering in this study. But we uh, our objective is to build an approach that goes from cradle to grave.
Okay, great. And related to this, we have a question. What sort of timescales are the life cycles calculated over? In terms of periods, maybe.
Uh, I don't know if I understood properly the question.
Uh, what sort of timescales are the life cycles calculated over?
The life cycle, the life cycles are. I think I understood. The life cycle is considering the 50 years old of the building.
Okay,
The time the lifespan of a building of almost 50 years old. So only the lighting system is replaced. So we for the installation we not consider the maintenance, because there is according to the environmental product declaration, there no need there is no need of maintenance for the installation before the 50 years of the lifespan of the building.
okay, clear enough. And related to the installation, Daniel was wondering if why ICB generates more employment than EPS. Is it got to do with the installation process?
With we Okay, this is divided in two steps. The first one is because all the impacts are bigger in ICB, because we are considering the domestic impacts of the technologies. So removing the imports, uh, all the ICB, removing the imports, we see that all the ICB is manufactured in Portugal, so all the impacts will be bigger, because the EPS, some parts of the EPFs are imported, so we are not considering that impacts. In the second step, we are considering, as all the technologies are built in Portugal. I think the the bigger number of employment is associated with uh, all
Production.
the indirect trades between the sectors until the production of the ICB, or since the removing of the cork of the tree and something like that. We are not going until now. We are not going deep in this justification, but we will see further. And it's a nice perspective we didn't thought.
Okay, and one last question because of the time, because this is related to multi-benefits at economy level, even at the local, regional, national level. Do you have any plans for disseminating information amongst local authorities or developers?
Yeah, our plan is just that, is to build this methodology to evaluate all the benefits, and uh, using some sort of a multi-objective approach, like multi-objective optimization. We are showing this to the local authorities to select the best portfolios of technologies that should be funded uh, with the Portuguese programs.
Great. Thank you very much, Marcus, for the presentation and for this discussion. And now we will jump in the next presentation where Daniel will speak about low carbon retrofit of UK social housing and overheating risk.
Good afternoon, everyone, and thanks for coming along today. My name's Daniel Kerr, and we're going to be talking today about retrofits in UK social housing properties and potential overheating risks from those retrofits and how we can mitigate and manage those overheating risks. So for some context, the UK is aiming to reach net zero carbon emissions by 2050, and to do that, we have quite an old housing stock in the UK, and there's a lot of retrofitting needs to achieve the kind of deep decarbonisation that will be necessary to achieve those net zero by 2050 goals. When we talk about retrofit in the UK, we tend to talk about common approaches such as internal wall insulation, external wall insulation, and also improving glazing and improving air tightness. In this research, we wanted to examine, in the context of a future warming climate, are there potential overheating risks from low carbon retrofits, particularly warmth focused retrofits such as insulation and improved glazing? So we wanted to identify the risks, look at the technical and behavioral measures that could be undertaken as part of the retrofit process and beyond the point of retrofit as well. And look at the kind of viability of these retrofit measures. So there are several definitions for overheating in the UK context. The Standard Assessment Procedure Appendix P deals with overheating risk in new buildings. ASHRAE 55 deals with residential and commercial properties, but the one that we're focused on is CIBSE TM52 and TM59 regulations. These are, TM52 is a design methodology for assessing overheating risk, and TM59 looks at residential properties specifically. Social housing is a key sector for looking at overheating risk because of the higher proportion of vulnerable residents. So this is elderly residents and those with existing health conditions. They may be more adversely affected by any potential health implications from overheating. And the associated risks of overheating include things like productivity losses, reductions in sleep quality, which can lead to other health complications, and also increased mortality. The big heat wave in 2003, for example, caused a lot of excess deaths in Europe. And at present, we're expecting about 2,000 excess deaths from heat stress in the UK, rising to about 7,000 by mid-century in a future warming climate. So let's have a look at some of the technical risks that lead to overheating risk factors. So really, it's the kind of stuff that you look at when you're looking at energy efficiency. It's the built form, boundary walls in between properties tend to increase overheating risks. Larger glazed areas will lead to more solar gains, which can increase heat gain in the property. Single aspect properties such as mid-rise flats and so on have higher risks due to less through ventilation potential. That's when you're opening windows on opposite facades of the building, so a front and a back window, for example. And south-facing rooms tend to receive more solar gains as well. Internal gains from equipment are also an issue, and occupancy. But ventilation is a key factor in terms of technical risks of overheating as well. If there's a lack of ventilation, then overheating risk is dramatically increased. And location is also a problem. For example, definitions of overheating from CIBSE provide definitions for London and Greater London area, and then the rest of the UK. So the urban heat island is very strong in London in particular. So in terms of the other types of risks, so what risks can be caused by retrofit and what risks can be caused by the user? Warmth retrofits tend to have some effect on overheating risks. In the literature, it says that retrofitting to 2010 standards in the UK will lead to overheating risk if there are no mitigations taken. Particularly internal wall insulation and floor insulation and increased air tightness are the main risk factors for overheating. But it's not just technical, and this is a key point in this research, is that the user is very much a participant in the home system. And we know this from warmth retrofits for energy efficiency, but it also occurs in overheating. So uninformed users may be unable to effectively manage their own overheating risk, and the ability of the user to manage their own indoor environment is also crucial in considering the kind of interventions that might be necessary, either behavioral or technical, to reduce overheating risk. For some regional context, we're specifically looking at the East Midlands in this research and cities in the East Midlands, and specifically social housing properties. One of the pieces of literature that was most informative in this research was Maury, Bayesy and Wright from 2020. They found that higher EPC band properties in social housing properties tend to lead to higher overheating risk. And this is because Higher EPCs tends to mean fewer air changes in the UK in particular. EPCs are energy performance certificates. They're a rating system for energy efficiency. And ventilation is a critical factor in reducing overheating risk. There are some definitions of what constitutes overheating from CIBSE TM59 there, 24 degrees C for 5% of annual occupied hours for bedrooms, for example. And yeah, there's a lot of violation of those standards happening. In terms of the national scale guidance, I feel like the guidance from the Zero Carbon Hub is quite important for reducing overheating risk. There's a hierarchy of measures. So you look at reducing the passive gains in the property and then improving passive heat rejection before looking at any measures that require energy consumption. So that's mechanical heat rejection, which is mechanical ventilation really, and then mechanical cooling like air conditioning is a last resort. But behavioral changes are available, and there are a lot of measures available at low to zero cost that can have a significant impact on reducing overheating risk and mitigating overheating. Changing which rooms are occupied at what time of the day, the use of internal or external shading like solar shutters or curtains, for example, can reduce heat gains into the property. That's all zero cost user. But we need to look systemically. A combination of factors contribute to overheating, and a combination of factors should look at mitigating overheating. There's no real one-size-fits-all advice here. It's very context dependent. So looking at behavioral measures more specifically, on the ways to mitigate, you can windows in the hottest part of the day. You can use nighttime for ventilation. You can switch off appliances that are not in use and all these kind of things. But we can look at delivery as quite important here. So things like web pages or advice lines. There's an analog with how winter heat advice is delivered to how summer cool advice could be delivered. And again, it's important to take vulnerability into account. Social housing tends to house vulnerable populations or more vulnerable populations than other tenancy types. So what could be done about that? We could look at an overheating risk assessment methodology, for example. At the time of allocation of properties, we could look at, are there any property-specific overheating risks? This could be done by the local authority, and then that could cause tenants to be more informed about the overheating risks they may face and the mitigations that they could take. So moving on from behavioral measures, we can look at the kind of technical measures that are available. There are some small-scale technical interventions that can be done at very low capital expenditure. These are things like window tints. There's an image of some tinted windows there that can block infrared or block some of the incident sunlight to limit the solar gains. And adding some shading, so that's curtains or shutters. It's not that common in Northern Europe, in my experience, to see external shutters on properties, but it's more common in sunnier parts of the world, like the Mediterranean. So in a future warming climate, we may expect that kind of design intervention to move northwards. Addressing internal gains is also important. This is things like hot water systems and appliances, again, making sure that they're sufficiently insulated or sufficiently efficient so as not to kick too much heat out into the environment. And then mechanical ventilation and mechanical cooling. They really should be considered as a last resort, because when we're looking at energy efficiency, we're looking at reducing energy expenditure fundamentally, but they may be necessary if there are particularly intransigent troubles with the construction of the property that can't be addressed through traditional mitigations. The important part of this presentation is how do we implement this, of course. Who bears the cost of these mitigations and how best to finance these mitigations? So through consultation with the local authority we've been working with, we find that match funding is the most common route. So the government will provide grants for energy efficiency improvements, and then the local authority will match those grants and implement. This looks like it's going to be the main kind of funding route for overheating risks as well. But in terms of the zero cost measures or the very low cost measures, we can look at the image on the right, for example, from Public Health England. This is an assessment checklist for local authorities or for landlords in general to look at the type of homes that are prone to overheating and the type of occupancies that are prone to overheating. And this is quite a useful communication route. Some retrofits are able to be conducted with minimal disruption and others very much less so. So things like internal wall insulation is going to be quite disruptive. But there are options to wait until properties are empty if IWI is the most appropriate measure. This extends the timeframes of mitigations, of course, so that's an issue. Communication is, as ever, vital. So ensuring that the technical retrofits are understood, if there are any, to mitigate overheating risk, and ensuring effective communication for behavioral change measures. So in conclusion, some locations are more prone to overheating than others, particularly through the urban heat island effect. Large UK cities like London, Birmingham, Glasgow, Manchester, etc., are more likely to see potential overheating risks than others. Higher EPC properties seem to be at a higher risk as well. This is because of the aforementioned challenges with regard to air tightness and increasing insulation. But it is possible to reconcile winter warmth with summer cool. And this can be done at zero cost or with short paybacks through technical and behavioral measures. For some more intransigent cases, it may be necessary to spend a little bit more on more in-depth technical measures, but there's a lot that can be done on the behavioral side already. And again, context dependence is quite important. Two properties on the same street may have different overheating risks, simply because of facing or because of occupancy or because of how the property system is operated. So it's important to use a kind of risk assessment procedure before deciding on what interventions are necessary. And again, there are analogs with keeping cool advice similar to how keeping warm advice in winter is delivered. It's important for the local authority to communicate what behavioral changes might be needed or what technical interventions might be needed to their tenants. So yeah, thanks for listening. A couple of examples of overheating mitigations from DMU here, which I'm happy to comment on, and any questions and comments, absolutely welcome. So thanks very much.
Very, very good approach, Daniel. Congratulations for this. Very good technical study. And I was wondering, because, yeah, you mentioned something, maybe it's a detail, but there is something very interesting. Higher EPC, the higher the risk of overheating is. But higher EPC, of course, it's a problem of if you let the heat in, it's very difficult to get it out, to take it out. But this is a matter of operation, and we are coming with the communication to the inhabitants, with the occupied, I don't know how, the people living inside, yeah. And I was wondering, not only for this particular aspect, which is communication and changing behavior of the occupants, but for the other measures, in the consultations with the landlords, how do you feel they perceive this kind of measures, this kind of studies, and how do you think it will be possible to change their attitude towards the minimizing the risk for the occupants?
That is a very complex issue, and particularly with private tenancy, there's been persistent issues in the UK with encouraging the energy efficiency of private rental properties. We've set minimum standards in the UK for EPCs of privately rented properties that have been pushed back against by the private rented sector time and time again. In terms of the social housing sector, it depends on the local authority. Some local authorities will be much more engaged with energy efficiency and with sustainability in general than others. The local authority that we've been working with, Leicester City Council, is particularly engaged with looking at increasing the energy efficiency of their properties and looking at the mitigations and problems that may cause in the future warming climate. So in terms of communication, it's about getting the information out there and making sure that people are aware. But the routes to communication, whether it's web-based or whether it's seminar-based or whether it's focus group-based or so on and so forth, that is still something that we're looking at as to what the most effective measure is. And integrating some kind of behavioral change theory is probably going to be part of the next phase of this research.
Yeah, we got some questions. I think there are occupiers who need help in managing overheating. Could it be communicated like hay fever warnings on the weather via TV with the keep it cool advice? Any thoughts on that?
Yeah, absolutely. I think something that people of my generation, shall I say, are a bit lax about is making sure the routes that aren't the internet are used to communicate things. My 80-year-old grandmother would probably not use the web to look at an overheating advice page, but she would see it on the news. So I think there might be a route to communicating whether it's a particularly hot day. I mean, the weather will communicate if it's going to be a heat wave, but they won't communicate that there'll be a risk of harm to health from particularly prone property to overheating in that regard. So I think as the kind of theory behind this develops, it may be useful to look at communicating with, say, local TV stations if it's going to be a particularly hot day, to look at the kind of mitigations, or to communicate the kind of mitigations that could be taken to reduce that, like opening the windows at nighttime and keeping them closed in the day, this kind of thing.
Yeah. And getting back with insulation level and increase and air tightness, we also have a comment. It's a matter of ventilation efficiency too, not only the insulation and air tightness. So it's again a matter not only of behavior, but of technology.
Absolutely. Yeah, the technical factors are probably more strong than the overheating factor, than the behavioral factors when it comes to the causes of overheating. And particularly things like property design have a very strong effect. Insulation and air tightness generally will cause overheating if they're tailored to retaining more heat in the property in a winter warmth context than in hotter periods. Then there's going to be issues with if you're not able to evacuate that heat effectively. So yes, it is an issue, and the technical measures do need to be considered along with the behavioral.
Yeah. We have a question from Matthew, but I will ask Matthew to ask it, because I don't want to read all I'm moderating, but I don't want to be the only person in the dialogue.
Hi, Daniel.
Matthew.
Yeah, I was interested whether you'd considered the use of thermal mass or materials with a higher thermal mass as part of a retrofit measure that might be used to help control or mitigate overheating.
I will say it's not something we considered in this research, because we were looking at the retrofit of existing social housing properties, and specifically looking at hard to retrofit properties like 50s, 60s solid wall properties. I know it's a big thing in the passive house design philosophy of having high thermal masses. And it's certainly a useful route to having that kind of heat soak that can be released in a more controlled manner. So it's something that I probably should have included in the technical measures, but it's definitely something that should be considered as a route to reducing the overheating, because it helps to just control the heat flux in general.
Super, thanks.
Yeah, so it's a good point. Thanks.
Thank you very much. Let's go to the next presentation. So it will be by Julie Goodhue and Matthew Fox about near zero defects buildings towards near zero energy buildings, visual defects via thermography.
Hello, my name is Julie Goodhue, and I'm really pleased today to be able to talk to you about our DVIS project with my colleague Matthew Fox. So DVIS stands for Defect Visualization Mid-Construction via Thermography. So the project is run and funded by CREDS, and the team are from the University of Plymouth and the Environmental Change Institute at the University of Oxford. And I've put the pictures of the academic team on the slide because they're in the room today and they may be answering questions on the chat function. So if you see their names, you'll know the connection there. So probably the best way to introduce DVIS to you is visually. So we've shown you a picture of a building site mid-construction, and the picture underneath it is the same scene in a thermal image, and we can see that the blue areas of the thermal image show where insulation has slumped after it was installed. So this is an energy critical defect that will confound efforts to reduce energy use, particularly in space heating. So DVIS is interested in spotting these and rectifying them before it gets to the end of the construction of the building, and also because they're hidden behind the finishes, we're interested in picking up those defects that are not visible by the eye but can only be seen in the thermal image. So the DVIS project is a research project, and we essentially have three branches to the research. The first is the thermal imaging, the technology, so it's a methodological research aspect. So how do we use the thermal cameras on site mid-construction to find defects? And then the second thing is, can we train site supervisors to autonomously check the work they're responsible for, and spot defects themselves? And how will that feed into a quality systems approach? Will they take what they've learned forward to future projects? And will there be a behaviour change angle? So will they do things differently going forward? So that's the sort of three branches to DVIS. I'd like now to hand over to Matthew, my colleague, who's going to talk about the first branch, which is the thermal imaging technological part.
Thanks, Julie. I'm now going to go into the first part of the DVIS project, which looks at thermal imaging and the challenges and solutions we've encountered as we've started to develop the methodology for this project. Thermography, or thermal imaging as it could also be known, is the detection of infrared radiation using a special camera such as a thermal camera. And what it does is it's detecting infrared radiation or heat emitted from the surface of an object, and the camera then converts this infrared radiation into a visual image which you're able to visually discern via the LCD screen. It's used in a range of different applications, but for buildings we've been using thermal imaging extensively to look for heat loss, and there are a range of different types of heat loss pattern that relate to specific defects. So I've got a range of different defects here. We've got up on the top left here, we have clear signs of ventilation heat loss, which is a typical draft where you've got the cold air coming in underneath the door, and you get this sort of fanning effect. We also have insulation or missing insulation, and you can see very clearly the defined patches where insulation is missing between the timbers in this image. Another area of heat loss within buildings is over here, which is cold bridging, which is very similar to the insulation heat loss, but more specifically in this image we've got cold bridging through a construction detail, where the cold is being bridged from outside, or the heat is flowing in the opposite direction. And lastly, we've got an image here which shows moisture ingress, and we've got dampness in a flat roof section of a building here. So thermal imaging is a really successful method of detecting defects, and quite specifically detecting defects that you might not necessarily have been able to visualize without the use of a thermal camera. So they're quite often hidden defects, and really useful technology. With regards to defects within a live construction site, we're particularly interested in how those defects come about. So what's generating those defects? And there are a range of different possibilities which are leading to those defects. So we've got defects through perhaps poor workmanship. However, it's not quite as simple as that. You've also got the potential for design-related issues, and maybe with all these innovative and technical or complex defect or details that are coming through, there could be a misunderstanding or a lack of expertise in how you can construct some of these really quite complex details. So design is also quite important, and then also the materiality with ever-increasing complex materials, whether construction workers are fully up to speed with how those materials should be installed correctly on site. So we really do need to think about how those defects are being generated. So the aim of the practical methodology through the DVIS project is to use site supervisors to inspect defects on site using a thermal camera. However, there are a number of different technical challenges that face us through this aim. The first of which is that construction periods don't always necessarily correspond with the cold season, And that's really important because we need to have at least a 10-degree temperature difference between the inside and the outside space. So we need to think about how we can achieve that whilst working on live construction sites that are inherently, generally quite open to the elements. There's also a critical aspect, which is the usability and the sort of the understanding of perhaps site supervisors to the defects they're looking at and the technology that they'll be using, and sort of putting the two together to try and educate them on how they can use thermal images to discern particular defects. And lastly, thermography itself is strewn with challenges and limitations. For those of you that are maybe familiar with thermal imaging, we've got material emissivity and surface finish, which is quite a critical limitation to the technology, and also climatic conditions. So we have to be very careful within the climatic conditions that we function within. And then there are other sort of more practical factors such as foreground or background obstructions. So these are some of the challenges that we need to really hone in on and address, and that's what we're hoping to do by proposing a range of different solutions for this project. So the first of which we have is selecting a suitable date for inspection. So we're going to try and choose construction projects where they're working on thermal parts or thermal components of the building over the cold season. And that's going to help us to really test the methodology that we're using. We'll also be looking at trying to seal sections of the building. And it might not necessarily be sealing the entire building, but maybe we can sort of focus in on smaller sections of a building and try to seal those up for inspection at a particular time. So we can time it and maybe phase parts of a building so that we can better undertake the thermal imaging inspection. And importantly, we'll be looking at using some form of artificial heating to warm up the building over a prolonged period, perhaps 24 hours before we get to site or before the supervisor inspects with the thermal camera. So if you can seal the building and then artificially heat it, we should be able to reach that 10-degree temperature difference, or even better, that 10-degree temperature difference across the thermal envelope in order to be able to get meaningful thermal images from the construction. I've also put in there ore cooling. So as part of the DVIS project, we're going to trial some form of air conditioning during the summer, and to see whether we can perhaps reverse the flow of heat during the summer from which you might expect during the winter months. So we're going to be trying something quite different there through this project. And another really important part of the jigsaw is the training of site supervisors. So the supervisors and construction workers will be trained by 2 Category 2 level trained thermographers. And we'll be going into things such as thermography physics, some of the limitations, and also defect identification, because anybody can use a thermal camera, but it's understanding what it is you're seeing through the screen and trying to discern those defects or looking for those patterns. And finally, we'll be using the same Category 2 qualified thermographers to review the thermal images. So there'll be that constant feedback loop, and if a site supervisor has any problems or questions, the members of the team that are qualified in thermography will be there to sort of help guide and to check on the progress of those surveys.
So thank you to Matthew. So we did say at the beginning that we have these 3 branches, so we'll now go on to look at the quality aspect of DVIS and the behavioural approach. The quality systems approach that we're taking then is to work with site supervisors who have, or their equivalent staff, who have responsibility for addressing building defects while the construction process is going on. So we see the cameras as a way of upskilling site supervisors in spotting some defects that might otherwise be not visible to the eye. And we're heavily influenced by other authors and researchers who've talked about encouraging a feedback or learning loop on site where new knowledge is managed and communicated back into the sort of quality system, So we're really interested in DVIS on monitoring that and collecting any insights on learnings. And we're asking, you know, would this be a little bit of a catalyst for that impacts on the culture of quality? So in terms of what people do after they've seen thermal images, we know from previous work with householders that when they were shown images of drafty homes, they were more likely to take action to save energy, to insulate or to seal the drafts. But that was with householders, so there's the gap in knowledge because we haven't done this with construction workers or site supervisors. But we know that after seeing thermal images, that they attract attention down to specific issues and new knowledges that weren't otherwise visible. And they're vivid and they're really not easy to forget, as they're easily recalled. And those things taken together drive motivation, or can drive motivation, and aid the formation of new goals, which in turn leads on to changes in behaviour and doing things slightly differently. So those are the positives, but on the other hand, images are never neutral. So people interpret them through their own prior perceptions and attitudes and beliefs. And we're aware that construction workers might be reluctant to focus on what might be perceived to be mistakes. And images are known to trigger defensive reactions. So an image intended to motivate could demotivate. So we want to make sure we design our approach so that isn't demotivating, quite the opposite. It's part of a normal pathway towards improved quality of construction. So at this point I want to hand back to Matthew, who's going to talk to you about some of our early learnings.
In developing the methodology for the DVIS approach, we were fortunate to be able to trial this methodology on 2 different construction projects mid-construction. The first is shown in the bottom left here, and this was where we went in and we identified pockets of missing insulation in the cladding system to this building. And these were completely sealed up, so you couldn't see it visually whilst undertaking a traditional defect detection exercise or snagging exercise. But when you went in with the thermal camera, it really did identify areas that needed to be addressed. Another example here was in the house at Plymouth University, and we artificially heated this large atrium space. And what we found was there was a perimeter of missing insulation or something going on towards the top part of this structure. And again, visually, you couldn't identify what was going on. So you really did need thermal imaging mid-construction to be able to work out where problems were in the building fabric. So we found that thermal imaging mid-construction was really successful. It was a proof of concept, and it certainly helped us to develop the methodology further, which we're going to be rolling out throughout the project going forwards.
So thank you for taking an interest in DVIS, and we've started a community board in the conference to continue the conversation. So thank you again for your attention.
Thank you, Julie and Matthew. Yes, I think it's very useful, this community discussion, but let's have some discussion first in here in the couple of minutes that we have. It's a very good approach. From technical point of view, I've noticed in your paper, you use the correct use of thermography, which is critical. Because as you said, it's not enough to have a nice and expensive camera. You have to know how to use it in order to take pictures and interpret and identify details. And this is leading to training of the site inspectors. You're in the first half of the project, I think. Did you have time to discuss with the on-site supervisors to see what is their perception of that, to see if they're willing to take a training, because it's not a couple of hours training.
Want me to answer that, Matt?
Yeah, you do that.
Yeah, I should have said actually at the beginning, because of COVID, we're a little bit delayed with our project. So, but we have started conversations with construction sites, and I think it seems to be there's two things at the moment. I think if you're looking at sort of passive house standards, they are. Some of them they're already doing sort of training of the staff anyway, so that would be part of that. And the other thing is they're bringing in teams of thermographers from outside and using those. So I think there are trade-offs one way or the other, you know, with the training. I don't think. I think maybe Matthew will talk more about this, but I think our training, as we've got it down to sort of key things that you can learn, and so that would be our focus, is the key things that we can learn, and then maybe the spotting where maybe extra investigation is needed. So key aspects that you can spot with the thermography, and then key things that maybe aren't that clear, almost like a medical assessment where you've got diagnosis and then something that triggers a further look or a bit more another way of looking at something. So I think we've tried to sort of get our training more organized like that. But of course, this is one of the things we're going to be researching and investigating. I don't know if Matthew wants to.
Yeah, sure, I'll jump in. So to train as a thermographer, so if you're going for your category 1 thermography training, then you're looking at about a week-long course. We're not anticipating training contractors or site supervisors for a week-long course. They won't become qualified thermographers. I think that would be impractical at this stage, but we're looking at something more along the lines of a day or maybe 2 days of intensive training, and then the sort of continued supervision of those practitioners. But you're absolutely right in terms of the training and site supervision is one of the key aspects of this project, and making sure that whoever's using the thermal camera understands exactly what they're looking at. And if they don't understand, there's lines of dialogue to be able to ask the question, you know, is this a particular problem or not?
Yeah, thank you. And if I may continue your parallel with the passive house course, for a designer, you have to pass, I don't know, 10 days, maybe 9-10 days course, and you have the exam. But after you take the certification as a passive house designer or consultant, that doesn't mean that you know how to design or to deal with a passive house. You have to design the first one in order to gain some experience. And of course, this is the same with site supervision. And yeah, maybe a couple of days of training would do it if it's combined with the on-site practical, let's say, continuation of the training. So not staying in a class 8 hours for 2 days, but yeah, having the gain in experience as a continuation of the education of the training session.
Absolutely, it's just like learning to drive. You gain an experience throughout the rest of your life, and it's just the same with thermal imaging. As a thermographer, I come across scenarios even now, and I'm sure that I'll continue to come across scenarios where you scratch your head and you don't quite know what you're looking at. So yeah, it's a continuing learning process.
Yeah, great. So thank you very much, both. We do not have any other questions, and I think we can go straight to the last presentation that I think will be challenging. It's about decentralized ventilation system with heat recovery as a potential solution to the centralized system for nearly zero energy buildings.
Hello, my name is Agneta Persson, and I'll present my paper, Hot Air or Real Solution, What Role Can Decentralized Ventilation System Play, to you today. I work for Emphasis, a consultant company working only with sustainability and circular economy. I'm also the president of eceee, and I'm the coordinator of BESMO, which is a network for energy efficient single family houses in Sweden. And the members are actors in the single family house sector, and it's funded by the Swedish Energy Agency. We know that ventilation in single family houses is a big problem in Sweden, and there are major problems with underventilation in the Swedish single family house stock. 40% of the houses are underventilated. And we know that from an investigation made by the Swedish Housing and Planning Agency. 15% of the Swedish single-family houses has at some point been investigated regarding moisture and mold problems. And houses with natural ventilation, which is the most common solution, but previously had an individual oil burner, get even lower airflows when the boiler is replaced with a heat pump. And that has been carried out in a lot of houses in Sweden. We also know, after calculation, that the energy demand on the national level would increase by 5 terawatt hours per year if we were to increase the flow to the standard or the norm flows in Sweden. And this may lead to an increased electrical heating problem, and it would also mean that it would add to an already existing problem with lack of peak power and grid capacity. This project stems from a project we carried out for new single-family houses, where we are looking into development of compact combined heating and ventilation systems for energy-efficient single-family houses in a Nordic climate. There were, of course, heat pumps on the market, and there were also ventilation systems with both exhaust and supply air and heat exchange. But they were over-dimensioned for the energy-efficient houses, and there were no combination of these kinds that were available for the Swedish market. So we have been carrying out a project that started already in 2014, and it has been a technology procurement that after that went into a joint technology development between the manufacturers of the equipment and the single-family house manufacturers. And we are now in a testing period where we are verifying the performance in real houses. This project led us to think of what can we do for existing single-family houses. And we know that it might be a problem when you're looking into upgrading ventilation in existing houses, but ducting can be a real problem. And it's also a possibility to use decentralized ventilation systems. They have a strong market in Germany, for instance. But there were no evaluations of heat recovery performance carried out under Nordic climate conditions. So we asked for money for a feasibility study from the Energy Agency and carried out a project where we were analyzing the potential of decentralized systems and are also proposing methods for testing, verifying, and developing decentralized ventilation systems for the Nordic climate. And the result of this study should provide a basis for the future work, and we are now looking into how to continue this. And you may know already what the decentralized ventilation system is, and there are different kinds. Here is a kind with ceramic heat exchangers, and there are several benefits from it. It's easy to install. You install it directly in the facade. There's no ducting needed, and it's easy to maintain as well. It has a low power demand. It has a high degree of heat recovery, and the suppliers say that it's approximately 90%. I'll come back to that in a minute. It can be installed in pairs to achieve balanced ventilation, and it can also be installed with wireless communication between devices. Here is a chart of the different components in a system, and here's also a drawing of a single-family house, how you can combine in pairs these kind of devices. And you need, of course, to look into what airflows you want and where you want the different kind of airflows when you develop these kind of system approaches. In the feasibility study, we looked at 3 things. We made a market analysis, we made a market intelligence survey, we made an analysis of methods for testing and verifying these kind of devices in the Nordic climate. And the market analysis included what systems are available on the Swedish market, what tests have been carried out on these, and are the tests carried out in a Nordic climate. The market intelligence survey was discussing how the systems and studies are tested and what have been previously carried out. And then we looked into the methods for verifying. And the study was conducted in collaboration with industry and academia, and the dialogues we had were involving suppliers of the systems, and they provided a lot of information during the work. And the results of the market analysis was that there are 7 types, or we identified 7 types of decentralized ventilation systems with ceramic heat recovery on the Swedish market. A challenge with the systems highlighted by both suppliers and researchers who have investigated the systems is disturbing noise levels. These noise levels means that there will be a risk that users in practice will reduce the airflow in the units, which means that it's then not fulfilling what it's aiming at. And there are no possibility to install decentralized systems in spaces that is not disturbed by high noise levels, such as basements or attics, since the systems are installed directly in the facade. We also found that there is a major lack of knowledge of how the system should be tested. And it's clear that it's not clear what standards or methods the system should be evaluated against when the products are launched in Sweden. The tests that are carried out on the systems have mainly been carried out by German suppliers at German conditions. And there is no common standardized methods for evaluating decentralized ventilation systems, only on a room basis available. And suppliers refer to different measurement or monitoring methods when accounting for the performance of their units. And this means that there's a need for development of comparable measurement methods. There is a standard that could be applied, but that's only on a room level, so it's not for a whole house. And when we looked at the performance and the research studies that has been carried out, we found 3 studies looking at it, and they indicate that the performance is under normal operating conditions, approximately 70% of heat recovery, which actually is much lower than the manufacturers and suppliers are reporting. But it could anyway be of interest to use these decentralized ventilation systems. They have a potential to be energy and cost efficient in cases where supply and exhaust ventilation with heat recovery solutions with ducting are technically difficult to install or too costly or are inappropriate in other ways. And in the diagram here, you see the results on the performance of the systems that have been investigated. And we also saw, when it comes to verifying methods, that an evidence-based study on how decentralized ventilation systems work in Nordic climate is needed. The products need to be tested both in a laboratory and by simulations of the Nordic climate. And it's also interesting to test the products in a standardized real case with the Nordic climate and compare between laboratory tests and real results, real monitoring values. And in a continued work, we are proposing the following aspect to be analyzed further: capacity, and at different pressure conditions against the appliance, function if filters are clogged, air distribution and at different fan positions and air mixing in the room, function if muffler is mounted to reduce the noise level, and also the actual noise levels. And there are several areas where decentralized ventilation systems need to be further studied, and there is also need for a technology development in order for the systems to be an attractive solution for existing single-family house owners in a Nordic climate. So we would like to look into, can these systems provide a single-family house with its entire ventilation need? distribution noise levels, the disturbing noise levels, sorry, how to handle them, risk of increased moisture load in the construction of a house if these are installed. And by initiating a project where the decentralized systems are properly evaluated, it can be clarified how the systems work under real conditions in the Nordic climate, taking into account the ventilation balance of a building, and also looking into if there is a risk for increased moisture load. And we propose also to have look into other ventilation solutions, and if it's possible to install on the outside of a facade, so it isn't having this kind of noise disturbance that is reported at the existing systems. And if you could install it on the outside of a facade, then it would probably need some changes when it comes to design and weather resistance. And we are proposing to the Energy Agency to allocate funds to conduct a feasibility study on how a technology procurement of ventilation systems adapted for existing single-family houses in a Nordic climate can be designed and implemented. Thank you for your attention.
Thank you, Agneta. I really enjoyed the presentation. In general, mechanical ventilation is not a popular solution in Romania. We are using natural ventilation, which is by opening the window, and of course this is not fit to implement the YNZEP building or to go to deep renovation without the indoor conditions complied. But yes, and we are raising the awareness on that very much. And there are occupants or designers that are proposing the decentralized system, part because of the cost, part because of the lack of possibility to have the ducts and the distribution. But I think that it's important to say that decentralized ventilation is not local ventilation. So we have to ventilate the whole house, the whole apartment, if it's a residential building. So in order to have that with local systems, we have to have a good design. So it's true, there is a problem of testing of performance, but it's also a matter of training the designers in order to serve the ventilation concept and not only the local, the room ventilation. And this is about putting together the different local ventilation in a system, just to prove the concept, to comply with the concept of ventilation.
Yes, I totally agree with you. And there's a need of increased knowledge about how the ventilation systems in existing houses is working. So this is one of the things that we want to aim at if we could continue this work funded by the Energy Agency.
Yeah.
And we are also including 2 of the university in Sweden in that work. So it's both the Lund University of Technology and the Dalarnas University. So we will be working, if we get the money to continue, we will be working both with manufacturers and suppliers and installers and the academia.
Yeah. And designers. I
and
think
designers, absolutely.
Very important.
Yes.
Matthew, please unmute yourself and put the question and the comment that you have.
It was more of a sort of a statement rather than a question, but I'm an architect as well, and I specified and designed decentralized ventilation systems previously. And I found, I think when you mentioned about the sound issue, Agneta, I actually have some behind me here. And we noticed the sound quite early on, but very shortly after we'd turned the system on, your brain kind of almost switches off the background sound. So you don't notice it at all. And I wondered, well, maybe this is a question. I wonder whether you kind of looked into that aspect, whether you looked at the ongoing use of these systems and how people maybe come to kind of get used to them, really.
Yes, and I guess it's a matter of where you place these devices as well, because if you need to ventilate all the house and have these kind of devices both in the bedroom and the living room and so on, then there might be a bigger problem than if you could only use it to support the ventilation you already have, because then you could avoid putting them in the bedroom and where you would probably hear it much more clearly when you're going to bed and going to fall asleep, and oh, that's the noise. So it's about the design of a system as a whole, and one of the things we want to look into is how can we maybe get hybrid solutions to the market as well. But it's nice to hear that you don't get annoyed by the noise any longer.
This noise problem is not only a matter of having the noise produced by the vibrations and by the air circulation, but also in this case by putting in contact the interior with the external. Isn't it?
Yes, it is, absolutely.
Because if you have a centralized system, then you have the hose, you have the ducts, and you might have silencers. And
yes.
yeah, on the other hand, with the filters and clogging and all the problems, it's more simple to deal it centrally.
Yes, there are pros and cons with those kind of systems, and you need to think of it from a user's perspective, so a house owner's perspective as well. It must be easy for them to maintain it, and that's a very important issue when you're designing the systems, of course. Yeah. But the main reason for us looking into it is the study I mentioned that the Housing and Planning Agency conducted some years ago, showing that 40% of all the single family houses have too low airflows, and that's of course causing a lot of health problems and other issues as well. So that's the main reason for looking into it.
Yeah. And if it's a centralized or decentralized system, it's a ventilation system, so it's putting into contact the internal environment with the external one.
Yes.
And it's a matter of penetration, and airtightness, I think, is very important. And this is relating also with the previous discussion on DEVIS, on using thermography. And let's join with Julie and Matthew the discussion. Did you include in your approach this kind of thing? So not only going to the thermal, to the insulation and to the defects, but also analyzing the airtightness of the penetrations on the ventilation part, for example?
Possibly. It's not something we've necessarily considered specifically with regards to the DVIS project, but certainly with passive house becoming more prevalent, we're starting to see a greater focus and interest in airtightness. And there's one school of thought that you undertake thermal imaging at the same time as the airtightness test, because you're positively or negatively pressurizing the space, and it makes identifying air leakage much easier to identify with the thermal camera. So I think, yeah, certainly that's something that we might look to try and incorporate as part of the DVIS project, linking up the airtightness testing with the thermal imaging. The trouble with that is the airtightness testing tends to take place towards the end of the contract when everything's been sealed up, whereas the DVIS project is specifically looking at mid-construction. So whether there's a case for mid-construction airtightness testing at the same time as thermal imaging, then maybe.
Which usually is the case, because it's if you want to have a very good test at the end, it's wise to have an intermediate test during the works.
Absolutely, but it's not a requirement over in the UK to have that intermediate test. It's only the very best projects that would receive that, and I think in those cases, the contractor team was slightly more switched on to kind of.
Yes, but we are coming back to the qualification of the on-site supervisor and the awareness. If he's aware that it's a very big risk to not have the performance at the end, he will do the mid-test.
Yes.
Yeah.
And there's also a difference between new buildings and existing buildings, which I'm working with here in this project, and it's much more difficult, I'd say, in the existing buildings, because then you have all the conditions already and you're trying to put a new system into it. So there are so many things you need to take into account when you design the system.
Yeah. Well, I installed 2 months ago, I installed a centralized system in my apartment, but I had the height and I had the space. But otherwise, I would go for decentralized one. Sorry, Julie.
Sorry, I was just thinking that my research is mostly with people and occupiers and behaviour, and one of the things that I've noticed over the years is that occupants often resist energy. I'm sure you know this already, but resist energy efficiency measures because of ventilation issues. So they like the airflow, and that's a reason not to engage with energy efficiency. So from my point of view, it's been really interesting listening to Anita and Daniel and Marcus and this idea of really enhancing ventilation and looking at the two sort of separately, so rather than conflating them into one and the same thing. So it's just an observation rather than a question.
And one thing to that is we often see people are trying to avoid the increased airflows by putting socks or something into the ventilation systems to make it go slower. The flow goes slower, and that's of course a very large problem if you are installing things to increase the flows and to increase the ventilation rate, and then the inhabitants just put things to destroy the flow again. That's really a problem.
Maybe it's a problem of control, but first from design. If the ventilation rate is really high, then could be a problem.
It's a matter of design in that case too, of course. It's about how fast are the airflows coming and what temperature are they coming with and all those things. And it's really something that needs to be developed much more. And also with the user in mind, so that it's going to be user-friendly systems.
Yes, because ventilation, ventilation, if we go back to the first two presentations, they are offering also multiple benefits for the health and for the comfort.
Yes.
And also a possible solution for the overheating in summer. Why not? Yeah. Well, so thank you very much. We are coming to an end. We have 1 minute left. And it will be, thank you again for this presentation, for the discussion and the session. I have 2 announcements to make. First of all, tomorrow we will have the last and maybe the best session. It will be in the morning at 10:30 with a panel 8 on buildings. It will be on combining smart building features for energy efficient buildings. And the second announcement is for the schedule after 20 minutes. After 15 minutes, 2 informal sessions will be organized both in meeting mode, so you can switch cameras and have discussions with your other delegates. One is an exploration of how sound and visualization can lead to a renewed connection to the energy system. And the other one looking at urban net zero and renewable energy commitments during COVID-19. And then at 6 o'clock, at 6 p.m., it's the summer study party. So check the agenda in Hoover for details and how to join to these sessions and to the party.
And the party is one of the most important things at the eceee summer study, so don't miss out.
Okay, thank you very much. Goodbye, everybody.
Thank you. Bye.